once I've come to love throughout my life. When the times are miraculous, when I stop to think twice, when I sleep in the bushes next to where the treasure lies. When the devil in the words that you speak to me, when there's nothing left and we are at the end. In the heavens, you laugh at me secretly, where it echoes over and over again. And there's nothing, no one that powerful, and the light that shines upon us as the sand. When I wake up, I'm doing a somersault for the ones who never dared to speak my name.
Officially 11:10. Let's go ahead and get started.
Recording in progress.
All right. Welcome, Data 100, another content lecture. This is our third lecture of the semester and the second Pandas lecture. So what did we see in the previous lecture? In the previous lecture, we went ahead and talked a lot about different tools that you can use in the data science lifecycle. What we started talking about was what are different data structures in Pandas. We saw what? What is the 2D data structure that we saw in the previous lecture? Data frame. Data frame. What was the two 1D data structures that we had seen? There was series and there was index object. So we saw how they're connected together. At the end of the lecture, what we started doing was actually data extraction. And I didn't have time to complete that part, so I'm going to continue from where we left off in the previous lecture. We're going to talk about how we can do data extraction using integer position, using square brackets, and then we're going to go a little bit deeper into more fun things. So today is going to be getting more practice in terms of what are additional functionalities that are available in Pandas so that we can do different fun things with a data frame. How can we add data? How can we modify data? How can we add rows? And how can we make conditional selection? So we're going to go a little bit deeper into Pandas. And a little bit of a content warning for today is that there's going to be a lot of different functionalities of pandas coming your way. So again, it might sound overwhelming because we're covering too much, but you don't need to memorize everything. As long as you remember the logic of how to use this stuff and how to make sure that there is a function that does a certain thing so that you don't need to loop over the entire data frame that you have. The whole purpose of us going through this API is that you know that everything can be handled in a vectorized way and you don't need to actually loop any time in during any of the homeworks and projects that you're working on, right? So just knowing that those functionalities exist is the job of us in today's lecture, and then we're going to go a little bit deeper into more complex stuff next week on Tuesday, but then you have the weekend to just get some rest and then have all of this content make sense to you before you come back on Tuesday. So let's dive in with what we wrapped up the previous lecture. Remember the lock operator. Lock, you can think about it as label-based extraction that we're doing. So we said that lock this L, you can remember it as, okay, why isn't it working? You can think about lock as label-based extraction, and you'll see later why I keep like highlighting that L in lock, because you will see I lock. So with lock, we're doing label-based extraction. What was label? Label is all of those bolded text that you see on all of the rows and on all of the columns. Where are they? So here we have all of the labels on these rows, and we have all of the labels on all of these columns. Labels are the ways that we are referring to each one of those columns and rows. We can manually provide label. We can manually provide label and index different rows that we have, or we could actually not provide names and labels, and then Pandas is going to automatically label stuff for us. So for example, here, all of the labels are manually provided. We said that, okay, there is a column year, there is a column candidate, and this was the election data set that we have been working on from the previous lecture, that these are all the candidates who ran for the presidency of the United States over the years, starting from 1824 all the way to 2020. That's the latest result that we have. And we can also choose to not provide the labels manually, and then Pandas is going to automatically label the stuff starting from 0 all the way to however many rows or columns that you have. So this is what we started seeing. With label-based extraction, we should specifically provide reference to the labels. Labels on the rows, labels on the columns, and then the intersection of that is going to be retrieved and be extracted for us. So we talked about different ways of doing it. We said that, okay, if you're providing the labels for rows and columns, you can provide those labels as a list. So you can provide a list of rows, a list of column labels, and then it will do the extraction for you. We talked about we can do the same extraction using a slice, right? So with the slice, we're providing a range of rows and a range of columns, and then it will do the extraction for us. There was one major thing that I wanted you to remember from the previous lecture was that when we're providing a slice to the lock operator, it is inclusive of the right-hand side, which is unusual with Pandas, right? Or Python generally. So it's always exclusive of the right-hand side. This is the only place that it's inclusive of the right-hand side. And then we also talked about, okay, there is also an interest in just doing a single item extraction, meaning that a single row or a single column, and then we would be able to do the extraction using that. So with iLock, we're following exactly a similar thing. The only difference is that now there is this I here, which refers to integer-based extraction. So what does integer-based extraction mean? Integer means that we're looking at the location of the item. What is the integer position? So if you don't know the labels and you don't want to bother with the labels, and you just want to, for example, go ahead and get the item at row 10, you don't need to know what label is associated with row 10, so you can just go ahead and extract that. Or column the same way. If you know that there is something interesting happening in column 2, you can go ahead and say that, okay, get me the second column. And the way that we can do it is exactly the same kind of principle that we followed last time. We can provide a list, we can provide the slice. Now a slice is working nicely similar to what we're expecting in Python, that it is exclusive of the right-hand side, and then a single value. So let's see some examples. if I want to provide a list, so I have to provide a list for both rows and the columns, right? So what is the list of rows that I'm providing? I'm providing the list of integer position 1, 2, and 3, right? So these are the rows that at integer position 1, 2, and 3. And it happens that integer position aligns with the label, right? Again, it's because our integer positioning starts from 0, and then the automatic indexing also started initially automatically labeled at 0. So it happens that when it is automatically labeled, the integer position and label values are going to be exactly the same. So don't confuse them. And then if you're saying that, okay, one column at integer position 0, 1, and 2, again, indexing or integer position starts from 0. That means that column 1, column 2, and column 3, or the first column, second column, and the third column that you're seeing here, that the first column was here, second column was candidate, and the third column was party. So the intersection of these two is going to be extracted for us using the two list items that we provided. One reminder from previous lecture, we said that always labels or the items that you're extracting and the rows are mandatory. So you have to provide what you want to extract, right? If you don't want to extract, or if you don't want to filter the rows, you have to specify that I'm extracting all. So you provide the colon, right? And then you provide whatever different list of columns that you want to extract. So here is also the same thing with everything that we're covering. It's that either we explicitly say that I want all of the rows, right, by providing colon, because that's also another way that we can specify that I want everything, starting from the beginning up until the end. Or you provide the list of the single row that you want to extract, and you can't skip rows. But you can skip columns. So here I can skip columns and then say that, okay, row at integer position 1, 2, and 3, but then I don't want to provide I don't want to provide a selection on the number on the columns, and it will automatically assume that you want all, and it will extract all for you. So this is the difference between how we treat rows and columns. So this again works similarly between lock and unlock operator. So slice works exactly the same way. So in this example here, I'm saying that, okay, what I want is that same rows at integer position 1, 2, 3, meaning that second row, third row, and the fourth row that I have right here. And then what it also says is that I want to extract a slice of the columns. Why do we want to use a slice and not like enumerate over that entire list? Because sometimes our column list or the row list is going to be very large, and we don't want to keep typing everything. So we can just say that start from 0, go all the way to 3, and not inclusive of 3. So here it is extracting column 0, column 1, and column 2, and not inclusive of 3, and that's where we're going to end. So you can use a slice for both rows, you can use a slice for columns, and then there was also another thing that we discussed, that if you don't provide the lower bound of this range, it starts from beginning. If you don't provide the upper bound, it will go all the way to the end. And that's why when we provide only the colon thing, it means that everything. It starts from the beginning, go all the way to the end. And that's what's happening here, that for the rows, we're specifically saying that give me everything, and this is actually everything. It starts from 0, it goes all the way to the 2020 row at integer position 181. Actually, that's, yeah. And then also, it says that for the columns, I'm going to do the selection. At integer position 0, 1, and 2 are going to be selected, and then 3 is not going to be selected. A reminder from previous lecture that when you see ellipses, that means that there are more rows that are not going to be shown to you, because it's just going to be a very messy output. So, a single value. You might want to get a single column. You might want to get a single row, right? Kind of seeing how much you remember from previous lecture is that when I provide a single label, say that, okay, I want a single column, what should be the output type? Series, yes, because a data frame is made up of different series objects, right? When I'm only referring to one column here in this example, I'm saying that give me column at integer position 1, which is technically the second column. It basically says that give me the underlying data structure, however you stored it, and it will say that yes, here is the output that we're providing you. This is a subset of that column because we also did filtering based on the rows. So this is only rows at integer position 1, 2, and 3. You can just double check that it says that this is a subset of the candidate column, and then the data type of the objects, the data type of the items in that series, it's object because it's a string. Someone came up to me at the end of the previous lecture, asked a really good question that I want to repeat here. They asked that, remember that I was saying that every time Pandas creates a copy of his stuff when we're doing any kind of operation, and it's not going to override the stuff over to the data frame, would that be the case with lock and iLock? And the answer is that yes. So everything that we're doing the extraction here is just going to give you a copy of, like not a copy, but it's going to create a temporary variable, and then if you're printing that and plotting that and whatnot, it will basically be a different variable that you're looking at. It's not going to be overridden over to your original data frame. So that's how it works. If you want to intentionally filter the data frame and override your original data frame, you have to specifically say that elections equal to this selection over the elections data frame, right? That's the only way that we can actually make things permanent. So I can also have a single value provided for both selecting rows and columns. So here I'm saying that row at integer position 0, which is the first row, and then the second column at integer position 1 is the name column. So it happens that in 1824, Andrew Jackson was the first candidate that was listed in our data frame, and that's what is going to be returned. And the data type is obviously going to be a string because that's the value that we're extracting. So we talked about lock, we talked about iLock. Why do we care about them so much, and which one should we use? Again, remember, lock was label-based extraction. iLock is integer-based extraction. Which one is easier to use? Most of the time you will use lock. So you will use lock because it's easier to like make sense of columns instead of you thinking about, oh, which column was candidate column, and then start counting from 0 and this is like integer position 2 or whatnot. You can directly say candidate, go ahead and find it, and then grab me the candidate column, and then that would be much easier. So a lot of time you will use lock, again, because it makes more sense. And also a lot of times it is more readable, right? So not only that it's easier, that you don't need to inspect your data frame before writing code, it is also easier. So you can directly write, for example, in this case, that I'm doing label-based extraction, grabbing all of the rows, and then grabbing year and candidate. So that's the way of doing it with labels, but with the, here is also extracting results. But then instead, if you wanted to do with iLock, you should do exactly the same thing, and then you have to go find out what those integer positions for those columns are. And it might get tricky sometimes because in like public data sets that you're working on, someone might wake up one day and try to like reshuffle columns, and then all of your indexes are going to be messed up, and like you want to get a result, but you're going to get a party. Right? So you don't want that. So a lot of times it's more reliable to use lock, not only that it's easier. But iLock is also helpful because we didn't waste your time talking about iLock for like 5 minutes here. iLock is helpful in a case that you have a sorted data frame in a certain way. So say, for example, you have a data set of moving earnings, and then you have earnings or movies sorted by the earning, and you want to find out, for example, what is the median earning of all of the movies in your data set. You would just directly index into the middle of the data frame, grab that earning or grab that movie, and then you'll be on your way, right? So things can be easier. Every time that you see me asking you on exam or on discussion handout or whatever that go ahead and find like the median of something. Go ahead and find minimum or maximum. One of the ways that you can do it is just to think about integer-based extraction, and then the data frame has to be sorted in some way so that extracting minimum or extracting maximum is easy, that it's either the first row or the last row, and the median is going to be always in the middle. So that's a very kind of interesting use case of it. So it was all making sense. Now I'm going to actually introduce a new thing that's going to be very complicated. But because as data scientists and computer scientists, we are often lazy when we're writing code. We always like shorthands for things. So there was a thought about, okay, you have like, you have unlike, you can do all of these extractions, and there were 6 different ways that we could use it, right? There is I, like, and lock that you can pick from, and there was 3 options for each one of them: list, a slice, and a single value, right? So 2 times 3 is 6 different options. And they sat down and they talked about, okay, which one of these 6 are most useful for people to use, and like how they're using it. Actually, it's more than 6. It's 12, and I'm going to tell you why. Because you have the option of choosing each one of those for columns or rows. It's 2 times 3 times 2. Sorry, this is like me doing the calculation on the fly. But anyhow, there are 12 different options you have. The most useful ones are the times, or the most frequently used ones are the times that you want to extract rows based on the number. Why number? Because a lot of time we don't care about the labels for the rows. We would, for example, say that go ahead and extract the top 10 rows, or go ahead and extract the row from 10 to 20. So you care about the ordering when you're talking about the rows. So that's why a lot of time when we're talking about using a slice, we would say that we want to slice row numbers, not row labels, right? When we want to extract a number of features. Say I'm interested in candidate and I'm interested in results, so that I see who won the election and who lost the election. There are 2 things that I want to extract and 2 columns that I want to extract. So every time that we are going to look at a list, we're looking at a list of column labels. Probably you care less about providing list of rows, right? You won't probably want to have row 10 or row, for example, 20 and then 25. That's like very unusual and not frequently used. But it is very frequently used that you want to extract a certain number of columns with the label. And also the same thing with a single column, a single label. Every time that you're providing a single value, not a range, not a list, it's more likely than not that you want to extract an entire column, an entire feature, as opposed to getting 1 row. If you wanted to get 1 row, you would just simply do I, like, lock, and then get that single row and be on your way. So with the square bracket notation or operator that we're using here, it can only accept these 3 inputs. Again, the 3 inputs are exactly the same thing that we had before. It's either a slice or is a list or is a single value, but it's context dependent. When it is a slice, we would say that you have to provide row numbers. When it's actually a list, it's a list of column labels. When it's a single value, it's again column labels. So kind of remembering this is going to take some practice, but a lot of us in practice use this because it's much easier to use it this way. So it's context sensitive, and we're going to see some example of that. So how would a slice of row integers work? So for example, we would say that in elections, I want to get the slice of rows starting from 3 all the way to 7 and not including 7, and this is going to be the result. So I don't want to specifically say which columns to provide. A lot of times is that you want to look at what's happening in a certain range of rows, and that's why you would just directly use this square bracket notation without lock, without iLock, and simply just using a square bracket, providing that range. It will automatically extract those for you. What happens if you start like giving a range that is not in your list? You will probably get an error, right? So you have to make sure that this range is like within the range of the elements that you have and the capacity or the size or the number of rows of your data frame. You have to have figure it out or like check that beforehand. When we're providing a list, it's always list of column labels. So for example, here, you're seeing that I have just this context-dependent extraction, and then inside it, I have this entire list. So this is how I'm going to like explain this entire thing, that there's 2 square brackets. One is for the list, one is for the context-dependent extraction. And what's happening is that it's going to go ahead, grab all the rows because you didn't care about the rows, and then you need to you specify that you want your candidate and result. So, a question for you. What happens here if I go ahead and say, okay, elections, and then I would say this is a square bracket notation, and I would say that, okay, let me try give the labels for the rows, and I would go ahead and say I want these 3 rows, 1, 2, and 3. What's going to happen there? Make a wild guess.
Maybe take the column position for those instead of the rows?
That was a good guess. Another one? Anyone else? Yes. The rows 1, 2, 3. So the trick here with context-dependent extraction, or this is square bracket notation, is that if you provide anything that's not a label in your column, it will just go ahead and it will try to do the key extraction or key lookup in a dictionary. Remember that our columns were dictionary. It will say that, okay, you gave me key 1. Let me go ahead and see if you have that key in your dictionary of columns. And it will go ahead and search over all of the columns. It won't find it. It will throw a key error. So you won't get anything. So that's why it's context dependent. And that's why it's really important that you know the use case of each one of them. When it's a slice, it's row integer. It expects integers. You can't provide anything else. If you're providing a list, it always has to be labels in your labels of the columns. Otherwise, it will throw an error. And then another thing is that a single column, a single value when you're providing, that's a single column, right? Again, same thing. If you provide any other label or any other value thinking that I would be able to extract a row, you will get a key error because that key doesn't exist in your list of columns. In this case, obviously, we know that because we're extracting a column, the data type is going to be a series object and will be on our way. Okay, how are we feeling so far? Good, not sure, bad, doesn't make sense. I need to see all hands up before I move on to the next slide. Good, sideways, down. Good, a lot of good. All right, so I am also monitoring questions here. So if you have questions, send us those questions on Slido. You can log in with that QR code and the code. So that would be the easiest way for us to take questions. Your wonderful PAs are here to answer them, and that's going to be very efficient. So why we use the square bracket notation or this context-dependent extraction? Because it's short, because we're lazy, because typing time adds up. So for example, if I wanted to say that, okay, I wanted to extract 1 column. So elections candidate, easily you'll get that series, you'll be good. If you wanted to do it with lock or iLock, say for example with lock, you should say lock. You know that you have to provide all of the rows, otherwise you will get an error. So you have to say all the rows, comma, and then provide the column name or the column label. So it's always longer. They do exactly the same thing, but it's always easier to use that context-dependent extraction that we have. All right, your turn. So which one of these following statements correctly returns the value bluefish in this data frame that we're creating? Scan the QR code if you're not on the slide already. Okay, 33, 42. When we say which one of the following, that's a hint that there might be more than one. So just look at all of the options. These are your options. last time the maximum participation was 860, I think. So I'm hoping that at least this time with the attrition we have 600. So I'm going to wait until 600 and then I'll move on. Hopefully you'll all keep coming to synchronous lecture and to the lecture to make things fun, or at least like see us go over this stuff and then watch the recording afterwards. All right, 600. So let's take a look at this weird data frame. So this weird data frame, we're creating it using a dictionary. So the dictionary has 2 columns because that's how we created a data frame using a dictionary. The labels for the columns, we're providing A and B, and it is shown as A and B. And then for each one of those columns, the values that are stored in that column are listed here. So for the first column, we're expecting 1 fish, 2 fish. For the second column, we're expecting red fish, blue fish. And we're interested in like finding out different ways that we can extract blue fish, right? So let's take a look at what's going to happen here. When I do iLock, that's integer-based extraction, right? So I will basically go ahead and say that iLock at integer position 1 for the row is going to be this row, and then for the column, it's also 1. So starting from 0, this is column 0, this is column 1. So we should be able to get blue fish. Running it, we're getting blue fish, right? So what's happening here? Lock 1 and 1. What's going to be the output? Yes, brave person. Exactly. And can you tell me what was the name of the error really loudly? Key error. So we're going to get key error because we're doing lock. We're saying that, okay, this is a label for the row. So we have the label, we're fine. And this is a label for the column, but do you see that label in the column? No. So it's going to give me a big key error here. So this is kind of easy for you to figure out. Every time that you got a key error, what's going on? There's like some label thing that you're not doing it properly. So what about this third one? So iLock, we're doing it on the second row. We're extracting second row. And then what are we extracting here? We're extracting a slice of columns, which is like all the columns. So technically here the output is a series of like thinking about like grabbing a row as a series object, and this is a series object with like all the elements in the second row, 2 fish and then blue fish. But we only want a blue fish, so that's not going to work out. So that's a not correct option. Then lock 1 and B. Is this what we want? That is what we want. So 1 is correct. We're going to go to the second row, and then B, the label for the second column is exactly what we want, so we have blue fish. Would this one work? I lock 1 and 0. So that's an easy no, because like the indexing is not going to be an error, but we're saying 1 and 0. So 1 goes here, and then 0 goes to the first column. So that's going to give 2 fish, hopefully. Yes, and that is not what we wanted. So we have 2 correct options, which this is not what I had there. I think this was changed. But anyhow, you got the explanation, right? I think Sarah maybe would change the options at some point. But anyhow, this is like my version of things. Question? There are more options. We can investigate them, but now you have the correct responses. Sorry, the poll was changed after I created the code. But you get the sense of why you might get key error, how to use lock, how to use iLock, and then how to use integer-based extraction and whatnot. So moving on to the next topic. So you might be asking me that, Nargis, we're interested in like doing label-based extraction, integer-based extraction, or everything. But what if there is a condition that I want to select rows or columns based on or values based on a certain condition? We had seen this in a series. So in the series scenario, we said that we can use Boolean expression in order to say that, okay, the rows that would correspond, or the elements that have the Boolean value corresponding to true are going to be included in the output, and then everything with false is going to be excluded from the output. The way that we can use it is that we can use the same kind of scenario that we have all of those Boolean values, and we can provide those Boolean values as indices to the rows, and then do the extraction using either context-dependent extraction, square brackets, or dot block. And we're going to take a look at that. And again, all the rows with true value are going to be included in the output. Everything else is going to be excluded. So in this case, I'm going to switch to a new data set. So this is a new data set of baby names. This is the data set from Social Security that has the name of the babies who were born in California, and the original data set has all the states, but we're looking at only California. From different years you're seeing, and then the state, we have year, we have also the name of those babies, and we have the count of how many babies with that specific name was registered, and then we also have the assigned sex at birth that is also reported on those babies. So this is kind of an aggregate data set on multiple different features, and then we're counting how many of those occurrences, of those combinations we have. So in order to kind of go over the rest of the topics here, I'm going to not look at the entire data set, but I'm doing a selection of only the top 10 rows. So I call the top 10 rows to be baby names first 10 rows, and then I'm saying that I'm doing the lock, getting all the columns and then getting rows starting from the beginning all the way to 9 and inclusive of 9, because this is a lock. And it gives me like all of those, the first top 10 rows. And then assume that I want to filter out or extract data in a way that every other row is included in the output. So the first row is included, second row is not included, the third row be included, and so on and so forth. So I want this to be there, not be there, not be there, and then all the way. So one way to do it is that I can provide some kind of a Boolean array object, which can be series, which can be list, and I can provide true. A Boolean means that the values are true and false, right? So here I would say that I'm providing all of those true, false values, and at every entry that you have true value, you would go ahead and say that this entry is going to be included. At every entry that there is false value, that value is going to be excluded, and so on and so forth. And this way, this Boolean list is going to help us to do the selection, right? It will do the selection, and then the output here in this case is going to be the filtered version or the extraction of those rows that I wanted in the original data frame, right? So we will follow exactly the same thing, but we want to do it a little bit more efficiently. But before I move on to show you how we can do it more efficiently, I want to show you how we can do it with also the lock operator, because here I did it with the context-dependent square bracket extraction, and I provided this entire list. So think about the list that I provided that has all of those Boolean values, and it is passed to a square bracket operator. I can do exactly the same thing with lock. So with lock, I can say that there's the lock operator, and then this is just the square brackets for the lock operator. We're saying that for the rows, go ahead and grab the rows based on this long condition of all of those true false values. Use that for indexing the rows, and then additionally, I'm saying that I want all the columns. And that's optional. I could just skip not providing column, and it would give me all the columns too, right? So two ways of actually providing a Boolean array type object, and then it will basically do the filtering for us based on the true false values. Or if I don't want to sit down and then just do true false, and manual checking all of those values, I can automatically calculate that. And we had seen an example of how we can do it on a series object. So in this case, I'm saying that what if I automatically create this Boolean series object with the condition that the sex of the baby be equal to F, right? So extracting all of those female babies, and then I'll have a logical, I'll store all of those values in this variable that is a series object. And what you can see is that for all the rows, automatically this Boolean expression is going to be applied. Each one of those rows is going to get either true or false, and then the result is going to be something like this, right? It will tell me that the data type is Boolean. So now we know that we can use that as a Boolean array type object that I can pass to either a square bracket or dot lock in order to filter those rows. So what I can do is now I would say that now I'm going to do the indexing. I'll go ahead and say that on baby names data frame initially, this is the entire data frame, right? Do the context-dependent extraction, and I'm providing you a Boolean series object that is going to be calculated using this expression that we already verified, that is going to have all of those true-false values. So in this case, again, the inside thing is going to be a series of lengths 400,000 something, and then the output of this is going to be the filtered version of the data frame, which only will have 230,000 rows, including all of those babies with the sex being equal to F, right? So this is the filtered version. You can verify the number of rows, you can verify the number of columns. All the columns are extracted, but all of the entries here have this condition in common. Okay, this is a little bit complicated, so that's why I'm going to go quickly to the code and try to do a certain thing. So here's how I load the data, and I'm showing you the head of the data. Remember, dot head, dot tail was the handy thing that we would quickly take a look at the top few rows and the bottom few rows. In this case, I'm calling head, I'm not providing any argument, and therefore it's just going to give me the top 5. And what I'm going to do is I'm just going to do kind of something similar, but I'm going to just double check for the name of a baby, right? So I would say that, okay, I'm going to create a series object that is going to be a Boolean series object. Actually, let me not name it. Let me just briefly say that I want, from baby names, I want to go ahead and say that the name column be equal to, say, Joey, and I want to see the result. So you're seeing that here I have a bunch of false and true values, and you are not seeing all the true values here because it just gave us a snapshot of the first few rows and the last few rows and not everything. What I'm going to do is I would say that I'm going to call this Joey condition. I'm going to store it, and then what I'll do is I'll say that, okay, now let's go ahead and take a look at the Joey condition. It's still the same thing, but now I have stored all of those series, all of those Boolean values in a variable that I'm calling it Joey condition. Are we sure that there is all true and false values in it? So right now we're only seeing false. We're not sure if there's any baby named Joey at all or not. One function that we'll see later today is calling unique. Unique is going to give you what are unique entries that you're seeing in this series. So one thing is that we for sure see false, but I want to see that if the number of unique items is 2, meaning that I have also true listed here or not. So here you're seeing that the number of unique elements is in fact true and false. So I have some entries that are true, but I just am not able to see them, which is good. So I'm going to go back. Now we have this Joey condition, and then what I'll do is I'll say that, okay, give me all the baby names. I'm doing the selection based on the condition that I had. So the rows that are going to be selected are the rows that are meeting this condition, or this condition is equal to true. So I would do this, run it, S, thank you. And you're seeing that, oh, in fact, we had some Joeys and over different years, and then this is the count of how many we have, right? So this is like a very powerful way of doing, of us doing the filtering based on different conditions. Obviously, we could do exactly the same thing with lock, and then also say that, okay, now we are going to get all of the columns or a selection of columns and so on and so forth. So it would basically filter it for us in the same way. So here's the condition that is still we're filtering based on the sex of the baby being equal to F. So one thing that you might be wondering is that, okay, what happens if I don't have a very straightforward condition, such as like the name being Joey or like the sex being a certain thing or not, but if I have multiple conditions? We can create compound Boolean expressions as well, using bitwise operators. So this ampersand here is going to be our AND operator, And then this vertical bar here is going to be our OR operator. So we can do AND and OR also on the expression. So you will have two separate conditions. You combine them using AND or OR, and hopefully you know what the result of AND or OR is when you're applying it to two different conditions. So what's happening in this case? Let's take a look. So I have a data frame baby names. I'm doing a selection. So that's my selection operator. And what's inside that's being selected or filtering my data is actually two Boolean expressions that are OR together. So there's OR between two expressions. What are those expressions? There's one expression here that says baby names sex equal to F. So these are all the female baby names. And then the second condition is that the year be less than 2000, right? So if either of those options are true, that the entry is going to be in the output, and you're going to see it here, that we have either some of the conditions that the sex column is F or the sex column is M, but the year is before 2000, and all of those are selected. So you can get creative, write different conditions different way. The only takeaway or like a wise point that I want to tell you is that make sure that you're always including all of those Boolean expressions that you're writing in parentheses so that like they don't get mixed up and you don't need to deal with the operator precedence and whatnot and remembering that. So in this case, it's super easy and clean, and you first calculate those two expressions, then you take OR, and then everything is clean. There are different bitwise operators. We can negate a Boolean expression. So say, for example, if you have a Boolean value or a Boolean array that's P, you can negate it using this tilde. So you can say tilde P. If it's true, it's going to be false. If it's false, it's going to be true. Or an AND, we already talked about it, and this is a caret operator, not carrot vegetable. This is caret, C-A-R-E-T. And this is bitwise, this is exclusive OR. So it's either P is true or Q is true and not both. So when both are true or both are false, the output is going to be false, but this is exclusive OR between P and Q. And you might want to use it in different places. But this is kind of a basic set of stuff that you need in order to write any condition that you want. Then you can do extraction based on a certain condition that you have. So let's just spend some time on this. Hopefully the options for this one hasn't changed. If you didn't get a chance to respond to the previous one, make sure that you respond to this one as well. And what we're interested in is to find out the first 3 baby names with the count greater than 250. And the hint for us is that that's the output on the right-hand side. So grab the right-hand side data frame however you want. Hopefully you're all logged in, so I'm going to go here so you can see the options. Okay, we'll start explaining. So I have this baby names data frame that we're all familiar with. I want to get somehow to this output. And it happens that this output is that the top 3 or the first 3 babies or the baby names with the occurrences of, or with the count being greater than 250. So practice with lock and iLock again. So when I say that I'm doing iLock, that's integer-based extraction, right? So the integer position happened to be aligned with the label, so that makes my life easier. So I'm saying that row at integer position 0, 233, and then 484. That's Correct. And then for the columns, we're saying that integer position 3 and 4. Let's take a look. This is 0, 1, 2, 3, and 4. So 3 and 4 is going to give me name and count. So that seems to be right, and that's exactly the same output that we want. This is one correct option. But what about the rest? So this should be an easy no, because we only wanted to have name and count. And here there is no selection on the columns. The only selection that we have is on the rows, right? And then with this selection that we have on the rows, we're getting exactly the same rows, but we get way too many columns that we don't want. With the lock, here I'm also writing the condition here, right? So the condition is that I want for the rows to be filtered to be only the rows with the count being greater than 250, which is exactly what is the condition that we wanted. Because it's lock, we can also provide a list of labels for the columns that we want to extract, which is name and count, so that's also good. But I didn't want everything under this baby names filtered version, but I only wanted the top 3. So dot head 3 is going to give me the top 3, so this is a correct option. This last one is very similar. So there's lock, there is the same condition, there is the same list of columns that we're extracting, but we're doing .ilock here. So this is how you can, in practice, you'll keep applying these functions back to back and keep filtering in multiple different levels. So that's pretty normal that I have this long line of code. But then ilock 0 to 3. Here it says that get me all of the columns. I'm happy with getting all of the columns because right now my columns are already name and count. So that's the good part. But the issue is with the ilock doing the range of 0 to 2. And ilock was exclusive of the right-hand side. So meaning that here is going to give me row at integer position 1 and 2. And that's about it, right? So in this case, you're seeing that I don't get enough rows, and that's the issue. But otherwise, mostly it was on the right track. So, and you got it right. And moving on. So I'm going to now go deeper into a lot of different functions. So every slide, almost from this point on, is going to be a new function. It's not going to be logic. So it's just throwing different functions and different kind of options at you. So say I want to write a condition. I want to compound this condition that I want to select names that not only Joey, but I want to get Bella, Alex, Lisa, and Nergis. And say that this list can be long, right? So it's really hard to write the condition and spell out all of those different options that you have. But Pandas has different kinds of easier way of implementing similar stuff. So the first function that I'm going to show you is .isIn. So .isIn, as you can see from the name, and Pandas is really readable, and the API is really kind of chosen those function names really well. It basically says that it's going to check whether something is in something else, right? So how can I make use of this? The way that I can make use of this is that I can say that I'm going to put all of those names that I wanted, remember Bella, Alex, Nergis, and Lisa, into a list. And then what I can do is I can go ahead and say that on the baby names name column, on that series object, check whether those elements are in the names list that I have. So very simple. The output is going to be, again, the inner side is going to basically check whether it is in or not. True, false, true, false, true, false. And then I can pass it to the context-dependent extraction. This is square bracket operator, and then it will do the actual task of filtering for us. So that's also another easier, higher level way of checking condition or creating more complex condition. There are also a lot of string functions. So I'm going to just show you, I think, a couple of string functions today, because a lot of time you have string values in the columns and you want to process them some way. But we have a whole lecture on how to process the strings, which I think is going to be lecture 6, if I'm remembering it correctly. But here, a stir that starts with, it basically says that I'm getting a column I'm telling you that this column is of type string. Dtss is saying that now I want to invoke a string function because you think that this is an object, but I'm telling you that this is a string. And then in the stir kind of library or the stir library, but there is a function that is called starts with. And then starts with is going to check whether the string, each one of those strings in that series is start with n or not. And the output here, as you can imagine, the inside is going to be a Boolean series, which then I can index and get the full list of all of the names that start with n. So there is a whole set of functions that are available in this stir library that we can use, and we're going to go over them later. So you might be asking that you're talking about selection, you're talking about filtering and whatnot. You did not tell us how we can modify it. So if someone hands us a data, we're just basically limited to just filtering it and just taking a look at the filtered version. You didn't talk about how we can modify it. And in fact, there are different easy ways to modify a data frame. We can easily add a column. So adding a column is as easy as like adding a key value pair in a dictionary. So how did you add a key value pair in the dictionary? You would just automatically say that I have this key and then provide the value. So it works exactly the same way here. We would say that I am creating this new column, just provide the key, provide the name. And I'm saying that the values that you're going to store in this column is going to be coming from this series object. So you have to provide kind of an array type value of the same length as the length of the initial data frame, and then it will automatically append that to the entire data frame that you have. But where did that baby name underscore lengths came from? This is what I calculated at the top here. And the way that I calculated is basically that I got the name column. I said that this name column is a string and get me the length of each individual one of them. So this function is going to go through the name column, calculate the lengths of each one of them. It creates a series object. It stores the series object into this baby name underscore lengths. And what I just need to do is to make sure that there is the correct reference added to the data frame. I'm just directly saying that create a new key, and this is its value. And it will automatically be added as an additional column to the baby names data frame, and you can see that it's added to the right-hand side. It's always by default is going to append from the end, so that it knows how many columns you added. If you don't provide, and then it basically goes from there. And you can also, there are different ways that you can shuffle columns if you want to, but there's no point because you're always referring to them most of the time with labels, and that's all that matters. So you add a column, so that's good. What if you have a data frame, you added a column or not, but now you want to modify it? You want to say that, oh, I calculated the name length, but maybe the name length that I calculated has a space in it, so I need to remove one from each one of those values that I had. So in the same way, we can do exactly the same thing. We can say that, okay, now remember that I had this name lengths column. Go ahead and grab the value for it from the value that I already had, just reduce it by 1. So again, every time that you're referring to a column like this, if it doesn't exist, it will create one. It will assign the value from whatever you're providing in the right-hand side. If it does exist, whatever you're providing in the right-hand side is going to override its existing content, right? So that's it's exactly how dictionaries work, and this is exactly how it works in pandas. So here, all of the name lengths is reduced by 1, and you can verify because mir is 4 characters, and now it says 3, so we correctly modified it. What if I give you a data frame, or you create a name for a data, you create a data frame or a column, and you're not happy with the name that you gave to that column? Maybe the label is too long. You don't want to keep typing name underscore lengths, and you want to rename it to something else. You can use .rename, and you can provide a dictionary. This dictionary is structured as all of those previous names or old names that you had, and then the corresponding current name that you want to assign it to. So for example, here I would say that, okay, I have baby names. I want to rename it, And then what I'm renaming is that I'm renaming columns. And then the previous value that I had for one column was name underscore lengths, and the new value that I want to assign, or the new label, is going to be lengths, or lengths. And you can rename multiple columns at the same time. So you just add another element to this dictionary, and then you should be able to rename multiple columns all at once. In this case, the output is just going to be that now I have lengths column instead of name underscore lengths. Okay. What if I want to drop a row or I want to drop a column? By default, Pandas thinks that you want to drop a row. So you call dot drop, it will go ahead and drop a row for you, and you will specify which row you want to drop. If you want to drop a column, you should specifically say that the axis that I'm dropping is the column axis, and then this way you can drop a column. So again, you can drop a row, you can drop a column, and this is a way that you can remove content from your data frame. So here I would say dot drop, and I'm saying that the label that you're dropping is length. Remember that this was a column. But if I don't say that this is from the columns axis, it will try to remove it using a label from a row. It can't find it, it will give you key error. So that's why you have to make sure that you tell it that this is a column that I'm dropping, because the default goes by rows. If you want to drop a row, you pass a label for the row, and then it will be able to drop a row, or you can also drop multiple rows at the same time. So in this case, I'm dropping the row, or dropping that column, and you're seeing the result on the right-hand side. Kind of exam point here is that notice here that I did everything in the right-hand side and I reassigned it to baby names. This is because every time that I modify or drop the stuff, it's going to be saved into a copy. It's not going to overwrite my original data frame. So I had to specifically say that override my baby names with this new version that has that column drop, and then it will do that for me. Otherwise, it will create a copy, and what you're seeing is that if you say dot drop, and then you print or plot whatever the content is, you will still see it existing there. So either you reassign directly in the same way that we did before, or you could say in place equal to true. If you say in place equal to true, that means that like do it in place. I know what I'm doing. Otherwise, they won't trust you. Cool? Okay. Hopefully, logically, everything makes sense. It's just so much things. But you have the weekend to just breathe and then look over them one more time. So now this is the promised 2 minutes break. We're going to go into more complex stuff. So stay for the second half, and then we're going to see more interesting things coming up. All right, we're starting in 5, 4, 3, 2, and 1. Okay, next piece. Some utility functions, as if like I haven't covered enough of the different functions. Now I'm going to talk about like what are different utility functions that are available in pandas, all the fun things. NumPy, everything NumPy is available to you. So say, for example, here I would go ahead and just look at all of the babies with name Yash. How did I do that? Here I am doing the context. I'm doing the Boolean expression here that the name is equal to Yash. So it gives me all of those Yash babies, right? And it's a data frame with all of those. And I'm only interested in the count of them. So that's why you see that I concatenated this additional selection, that if you think about this as a data frame, on top of that now I'm also indexing and getting only one column. So this is context-dependent extraction and extracting only a single value, which was extracting a column. This is the first time that you're seeing two square brackets next to each other. This is not like a 2D array thing that you had seen in different places or like in Java or things like that. But this is like that. I created a data frame. Now I have it. Now I'm keep indexing into it. So you can keep adding those square brackets next to each other, or like .lock and .ilock back to back. But anyhow, so I have a series object with all of those counts. And we know that those counts are counts of all of those entries with baby name equal to Yash. So I named it as Yash count. So we can do all the NumPy stuff that you were doing in data 8. Those are coming from data 8. But I can say that np.mean pass this series object, and then it will automatically calculate the mean. I can get the max. I can do anything under the moon that like you've seen in NumPy. So everything can be calculated. There are other utility functions. There is size, shape, and all of those things. Some of them you've seen. I gave you kind of a blurb of unique. I gave you the blurb of, I think, shape once. But let's take a look at them quickly. If I have a data frame, when I say .size, .shape, it will give you the number of rows, and it will give you the number of columns, right? So that's easy for you to figure out how many rows do you have. If you want to provide a slice and like get the slice and making sure that you're within the range, so that's an easy way to get the dimensions or have a sense of the dimensions or the size of the data. If you're interested in just knowing how many entries could possibly be in your data frame, you could just call .size. .size is technically the capacity of the data frame. It's number of rows times number of columns. And if you don't trust me, if you multiply 5 by that 400,000 thing, this is the number that you'll get. So it just doesn't care about the values that are stored, it just is a capacity thing. Describe is going to give you, when I call describe on a data frame, it's going to only look at the numerical columns. So here the numerical columns that I have is year and the count, right? And it will give me some summary statistic about those columns. So it will give me, okay, what's the count? How many actual values do I have? Because you might have missing values. It will give me like average, a standard deviation, minimum, maximum. It will also give me quartiles. I'm going to come back talk about all quartiles, I think, lecture 7 and 8. So when we are doing visualization, we want to visualize distributions, so it's going to be fun time that we can visualize min, max, and all the quartiles. But anyhow, we're only looking at year and count because those are the numerical columns, and then we get some information. You can always get really useful information from Describe. I think I used it in the demo in the first lecture where we were looking at, I think, what was that? I don't think that I used it, but anyhow. So here in this case with the year, if you're looking at the maximum, you would be able to tell how updated this data set is. So you know that the latest update on this data set was the year 2022. So any baby who was born after that is not included in this data set. So these are all the sanity check stuff that we want to do before getting into feature engineering and modeling and whatnot. If I call .describe on a series object, so here I'm getting the series object only one column and just calling the .describe. In this case, what I have is something is slightly different, but it just describes something, and that's how Pandas is implemented. So what you're seeing here, okay, this doesn't work. Next time maybe. It tells me how many elements I have. It still gives me a count. It tells me how many unique elements I got there. and then it will tell me what is the top frequency of those unique things that I had. We know that it's F and M, and it tells me that F, or female babies, are more frequent entries in the data frame, and then it will tell me that the frequency of female babies is this much. So that's how it's implemented. We can also sample from a data frame. So there is a whole set of lectures that we're going to talk about sampling a data frame and just looking at the distribution and whatnot. So in order to sample data from a data frame, we can use .sample. So very creative. With .sample, it always assumes that sampling is without replacement. So there is a chance that you sample multiple times back to back, and then you will be able to sample the same thing. Or you sample 5 entries, and then you get 1 entry twice. So it is with replacement by default. It is without sorry, it's the other way around. If it's without replacement, that means that you won't get the same data multiple times. But you can set that replace equal to true, so you make it with replacement, which in that case you should be able to extract same entry multiple times. Then you can also apply lock and iLock and all those things on top of that, and then get more useful information. So if I call .sample, randomly will give me 1 sample. If I call .sample 5 and provide an argument here, this means that I want 5 elements. So sample 5 entries for me. And then on top of that, I'm saying that, okay, now that you gave me this data frame with 5 samples, I want to index into it. I want to index into it and then say that I want all the rows, so keep all of those 5 entries that you gave me, and then give me columns starting from column at integer position 2 all the way to the end, which technically means that if this is 0, this is 1, this is 2 all the way to the end, means year, name, and count are going to be included, as you're seeing here. We can go more complex and keep adding stuff on top of each other. I can say that let's first go ahead and filter these babies so that I'm only looking at the entries in the year 2000, right? And then sample from the babies in the year 2000. So a lot of time when we tell you a certain condition, you need to think about what makes sense and what order you should apply stuff, right? So that you're sampling from the right distribution. So if you were like doing the filtering afterwards, then your sampling was not going to be correct. So here, in order to make sure that my sampling frame is correct, I'm filtering based on getting the year equal to 2000. Then what I'm doing is that I'm saying that sample 4 instances for me, and then replacement is allowed in this case. So it does it with replacement. After you're done, after you gave me 4 samples from the year 2000, then I'm doing an additional thing where I'm saying that give me all of those rows, but only give me the same columns, year, name, and count, and this is how it's going to look like. Okay, so we can keep adding these functions together. I think I've said it enough. You know it. We do it. Value counts. So value counts applies to series objects. So when we're calling value counts on a specific column, the way that it will work is that it will calculate the frequency of each unique occurrences in that specific series object. So for example, when I say name.valueCounts, it will basically go ahead and calculate or find out all of the unique names that we have. So these are all unique. You can't see 2 rows with the same name. And then it will tell me that what is the frequency of each one of them, each one of those values. There's a note that this frequency thing is different than count, right? Every row which had a count is counted as 1 occurrence. And then we're just counting how many times they appear, which technically here means that, I think it means that how many years was it that a baby with this name was born, right? Kind of, sort of, I hope, because that 223 is a very large number. But anyhow. We can also, we've seen unique. Unique is just that, like, if you don't care about the frequencies and you care about the values, you should just call unique, and then it will give you an array with all of those unique names. So that's what I did when I wanted to make sure that there is a true instance there, that the babies are named Joey for fact, and then we moved on. We can actually go ahead and sort values. So remember that I said with the movie earning thing, if you sort them, then you can get the median earning. So a lot of time, if you want to do something like that, And if they tell you that the data is sorted, you just sort it again, don't trust them. Or if it's not sorted, you still sort it and do your own thing. So sort value, when it's called on series, is very straightforward. It will automatically sort all of those values based on the expectation of how sorting works for that data type. So for example, for a string, sorting works in alphabetical ordering. So all of those letters are going to be ordered alphabetically, in alphabetical ordering. So here, sort values, you see, we're starting from Aiden and then go all the way to the names that are starting with Z. So by default, the order is in ascending order, not in descending order. If you want the order to be descending, you have to set the parameter that you have, say, ascending false, so that it sorts them descendingly. If we want to sort a data frame, that's a little bit complicated. Again, here's when logic is going to be very helpful. If you want to sort a data frame, how would you want to sort it? You just need to say sort by what, right? Because you have a bunch of different columns. So that's the only difference. Here you should say sort by what, and then it will go ahead and sort by that thing that you said. So here I'm saying that baby names is my data frame, sort values, sort by the count column. You can provide two columns. You say sort by this first and sort by this other one second. That can be complicated, but there is functionality in pandas. And then here we're saying that ascending false. I don't want it ascending. I want it to be descending, so that at the top I see the most frequent kind of years that any name had appeared, which looks like that there was a substantial number of babies named Michael in 1950s, and that's the maximum frequency kind of that we see. So you can do all this fancy stuff with data frames and all of those functionalities. Again, we don't want you to remember them, but we just want you to have heard about them so that you can keep using them in the lab and homework, and then you know that they exist. You can go back to the API, find them, and then use them. So I want to quickly show you that we can get creative. We do not need to rely on pandas to do all the things for us. We can say that, okay, I want to do custom sorts. I don't want to do sorting ascendingly or descendingly by the name. But say, for example, I want to sort by the length of a name, right? And sort all of those values based on that. So I'm going to just show you. These are not things that you haven't seen before. There's a couple things that you haven't seen before, but these are mostly techniques. So if I want to say that I want to sort my data frame based on the lengths, what I can do is that go ahead, create a column, name lengths, and calculate all of those name lengths values. How do I do that? You had seen it before. I said that go ahead, grab the name column, assume that it's a string, calculate the lengths, store it in a series object. Now we went ahead and created a new column and then assigned those values to that column. And then here we're just sorting the data frame by that column that we created, right? Very simple. So this is for you to think about what functionalities did you know, and then how can you create them. And then once you're done with this column, you can drop it afterwards. Once you've sorted everything, you can drop that column and then reassign the values. We can also use a key argument. So here we would say that I want you to sort values, and I'm telling you that sort by name. But don't sort by name based on the data type of a string that sorts based on alphabetical ordering or the encoding of those strings. But instead, I want you to sort it based on this key argument. This key argument says that every time that you saw an instance, the order of this instance is going to be calculated based on that lambda function that we're creating on the fly. That lambda function says that once you have a string, once you have a series object, what you're going to do is that assume that it's a string, get the length, and that's going to be the priority or order of this string value or that entry. And then it will basically try to sort the entire data frame by the name using the priority that this key argument provided. So think about key as providing the priority that overrides the initial data type priority. And the last fancy way of doing it, which I think is going to appear in only one of the homeworks, but it will appear somewhere that you don't expect, but it's something that you really need to remember, is that I can actually go ahead and create a column. So here I'm creating a column, say dr_ea count, because I want to count how many instances of dr and ea exist in each one of those names, and then sort names based on the frequency of dr and ea in that, which is kind of crazy, but it's kind of a made-up thing to go over this complicated example. So I'm creating this column. I'm saying that the values in this column should be calculated using the name column, initial name, and then what I'll say is that go ahead and use all of those values and apply the function dr_ea count. What is that function? That function basically says that, okay, when you get a string here, go ahead and count dr, go ahead and count ea, return that value. So what it does, that line of code, is that every instance in each one of the rows, it will go ahead, get that string, pass it to the function, map that function into that string, get the corresponding value, store that value into the column that I created. So then I'll have this drea count, that the only thing that I need to do afterwards is just go ahead and say sort values by this in ascending, and we'll be on our way. All right, cool. I mean, we still have 3 minutes, but I'm going to let you go, and we're going to go ahead and talk about grouping in the next lecture. Thank you all for coming along. We'll see you on Tuesday.
Record.